Good morning. Let's start the class. Okay. So today we will continue our discussion on this predicate calculus. And then let us do a very quick review of the two concepts that we have introduced last time. So we have talked about propositional function. So for instance, x is greater than 0. And this is a propositional function. So if it is standing alone, it is not a proposition because we don't know the value of x. But once the value of x is inserted, when this is fixed, then we know that this becomes a proposition. We can know this will either be true or false, but not both. Is that okay? So it depends on the value of x to get a truth value. So we can denote this by a symbol. Let's call it p, but then it is based on x. So it looks like a function. Whenever we fit x inside, it will give us some output. So this is the concept of a function. Is that okay? So it is a function to generate proposition, so we call it a propositional function. Okay? Now similarly, this one is also a propositional function, but this time we have two variables. So x is the mother of y. So unless I tell you what are x and y, when these two are fixed, then we still do not, so unless I have fixed all these, otherwise we do not know whether this is true or false, because x and y, there are variations. But when x and y are fixed, then in that case this becomes a proposition, and then we know its truth value. Is that okay? Okay, now we have also introduced some quantifiers. So there are two quantifiers that we have talked about. One is for all, and then the other is there exists. Is that okay? When quantifier is combined with a propositional function, we can make it into a proposition as well. So let's take a look. So the simplest one is, so we have talked about two types of method to combine quantifiers with a propositional function. So for instance, this is the first one, for all x, px. Okay. So originally, px is just a propositional function. But here, if we add this for all x there, then this means what? We need to consider all the possible x's. Check the value of px and see if they are all true. Is that okay? So if they are all true, then we say true. If one of them is false, we say false. Okay? So that's why this becomes a proposition now. This is not just a function. A function is we don't know which value of x we should insert. But here, we check all the possible x's. We look at everyone, so no x escaped. So we look at all the x's, check the px, and then get the true value of each case, because we look at each x one by one, so the true value is known. And then see if they are all true. So if this is the case, then this is true. Otherwise, this is false. Is that okay? We have also seen this one. So there exists x, px. Now the same. This one is we will be checking for all the possible x's to see if any one of them will get px to be true. If one of them, or more than one of them, will give px to be true, then we will say true. Otherwise, we will say false. Is that okay? So here we are examining all the possible x's as well. So it is not just a standalone function. We know all the x's will be needed, and then they are seen. So this becomes a proposition. Is that okay? Good. But then this is just a single variable case. So how about this one? So let's say I have a q. Okay, so q xy. So for instance, I can write down something like q Mary, and then maybe this is Jesus. Okay, Jesus. Okay, just an example. So let's say Mary is the mother of Jesus. Let's say we have something like this. I don't know whether this is true or false. Maybe it is true, maybe it is false. But I know that this is a proposition, because now it is already fixed. This is some person, this is some other person. X and y are fixed, then it is a proposition. Is that okay? Now similarly, how about this one? So there exists y, q, Mary, y. Okay? So here, what does it mean? Okay, look at it. It means that It means what? It means what? It means to determine. So this looks like a propositional function, right? And then if we look at it, Q marry Y, it says that Mary is the mother of Y. And then if we combine this with there exists Y here, so there exists someone, such that Mary is the mother of that person. Okay. Is it a proposition or is it a propositional function? Do we know? Do we know the true value of this one? Yes, it is now fixed. We may not know exactly the true value, but we know that it is a proposition because we will be checking for all the possible Y's to see whether Q Mary of that Y is true. Okay, we look at each different Y, and if one of them gives us Q Mary Y to be true, then it is true. Is that okay? Is that okay? Okay. How about this then? For instance, there exists Y, Q, XY. Now, this time, even if we are combining this one with the there exists, we are combining QXY with there exists, we will find that we don't know what we are checking. We are checking for all Y, whether QXY is true. But then you didn't tell me what are the x that you are going to consider. Is it a particular x or is it all x that we are going to consider? We don't know. So depending on the x that we insert into it, we will have a different value of this one. Is that okay? So this time, although this looks rather strange, but you will see that when I give you the value of x, you know that it is a proposition. But if I do not give you the value of x, it is still unknown. So you can think of this as something like a certain kind of a proposition that depends on x only. Okay? So it is rather strange, but then you will see that once I insert x inside, then it becomes a proposition. So this one itself is a propositional function, but the variable is now just on x rather than the original x and y for q. Is that okay? So this is a rather interesting concept. If you are okay with this, could you please raise your hand? Okay. If you need a little bit more time, could you please raise your hand? Okay. Okay. Okay, so this is good. And what is the reason? What is the reason? Okay. The reason is that, what is the reason that it is not a proposition? The reason is that for this proposition, we just talk about how y is considered. Okay? So in that sense, y is something we call it a bound variable. So it cannot move. It cannot move anymore. For this y, the view on this is we look at all the possible y's. Okay? Now similarly, for this one, this is also a bound case. The value of y is bound. So this one looks at all the possible values of y. This one just looks at a single y, which is Jesus here. Is that okay? Now similarly, for this one, this is also bound. So this is original x. Okay, x can be Mary, John, Peter, Paul, whatever. But here, we fix x to be Mary. So this time, the x value here is also bound. So when every variable of the propositional function are bound, then this becomes a proposition. Otherwise, if there is something that is left unbounded, or we call it, this one, we do not bound it. This is called a free variable. If something is free inside a propositional function, then it is still a propositional function. Is that okay? But you will see that it will change a little bit. Okay, originally x, y are both free, but once y is bounded, then it becomes a new propositional function that depends on the free variables only. Is that okay? Okay? Okay. So in that sense, we can do something very interesting. Okay. So look at it. So this is there exists y, q, x, y. We know that this is a certain kind of a propositional function on x. Okay. on x, this is a certain kind. So you imagine this is something like Sx in our mind. Okay. Now, there are different ways to bound this variable x. You can insert a specific value, or we can use quantifier, right? So for instance, I can use for every x to put inside. So for every x Sx, so this is like for every x there exists y qxy. Okay, and for this case, all the variables here are bound, and this becomes a proposition. Okay, is that okay? Now there is something very interesting. Okay, so now we will see that in a proposition, this is a proposition. So this is a proposition. There can be more than one quantifiers. So here there are two of them. So if your propositional function is even longer, may have originally 3 or 4 variables there, then you may have 3 or 4 quantifiers attaching to it. Okay? So, but then remember, okay, so this is very, very important. The ordering of these quantifiers are very important. In general, we cannot swap the ordering. So for instance, let's use this qxy as an example and understand the meaning of the two different ways of writing, let's say. So for instance, I can say for every y, there exists x qxy. Is that okay? So this is one way. So I'm using for all y, I'm using there exists. Okay? Now let me switch the ordering a little bit so I can create another proposition like there exists x for all y qxy. Okay? And take a look of the meaning of these two different things. Okay? So so what I should do is there should be a bracket here. But since there is no ambiguity, so this bracket can be removed for shorthand notation. But let's go back to look at what is the meaning of for all y there exists x qxy. So it says that for every person y, for every y, right, there is some person, I call it x, such that x is the mother of y. Does that make sense? So everyone has a mother. This is saying. Right? For every person y, okay, there you can always find a certain person, let's call it x, such that x is the mother of y. So it is just in English, plain English, it is saying everyone has a mother. Is that okay? But could be more than one mother, but at least one mother. Okay, there exists. Okay, everyone has at least one mother. Okay, so this is the meaning of this one. Okay, the first one. This is the first one. The second one, what does it say? The second one says, there exists a person, let me call it x, such that this person is the mother of all person y. Okay. So this may not apply for human, maybe. This may apply for bees, maybe. Okay. But bees, there could be some problem because who is going to be the mother of the queen bee, right? So suddenly, this has a different meaning, okay? So for this to be true, so for the first one to be true, it is easy. Yeah, because normally we understand that everyone has a mother, okay? But for the second one to be true, you need to find a supermom such that it gives birth to everyone, including herself. And then this is unlikely to be true, okay? Okay, so you will see that just by swapping the ordering of these two, there exists and for all, the meaning of the proposition could be very different. So this is the key point to remember. But it is not, okay, for all there exists, okay, you cannot swap. But there exists, you can swap. So if someone write down there exists x, there exists y, so let's call it a proposition R xy, then we can swap. If they are of the same type, there exists, we can swap. So you can convince yourself why this is true. So for this one to be true, the only case is there is certain x, there is certain y that you can find such that our xy becomes true. Is it okay? And if it is the case, it implies that you swap the ordering of choosing x and y, you still find that xy. Is that okay? Is that okay? So there exists, we can swap. And similarly, for all x, for all y, if they are of the same type, let's call it t, xy, then we can also swap. For all x, for all y, it's the same as for all y, for all x. The reason is that for all x, for all y to be true, you need to consider all the possible pairing of x and y's. If all the possible pairings are okay, then you look at the pairing in a different way. You choose y first and choose x later, but you still look at all the possible pairings of x, y. You still check the same set of the same number or the same collection of t, x, y. And you need the same collection to be all true, for all the things to be true. So in that case, this means that they are having the same condition to be true. So they are equivalent, logically equivalent. Is that okay? So there exists, you can swap. For all, you can swap. But there exists for all, you cannot swap. So this is called a scope. Scope of a quantifier. Okay. So if you still remember, when we talk about logical operators, we have talked about something called precedence. We have talked about something like precedence. Not is to be applied first and or later, and then this one later. Is that okay? So for instance, if I have some proposition P and some proposition not Q, and there is some proposition not P and not Q, something like this, we can understand that not P is applied first, not Q is applied first, and then we apply this and later. Is that okay? So in that case, we don't need to have bracket to be specified. Okay? So here, when we have for all that exists, it is applied at for all that exists should be the highest. Okay? Okay, this has higher precedence than any logical operator. So in that case, this is the px, right? And then we will combine this with this one. And this one is a standalone thing. And then we try to AND them together. Is that okay? Now, so in that sense, this is still not a proposition. Okay? Because the x here, for all x, is attached just to this one, very closely to this one. It cannot cross this n. So this n is of a lower precedence. So we cannot cross this n. So in that case, this x is bounded, but this x is still free. Is that okay? Okay, so good. So if you really want to choose for all x such that at the same time px and qx to be true, then we should write something like this. Is that okay? But on the other hand, if you want to say for all x, px is true, and for all x, qx is true, then in that case, we should write something like this. Is that okay? And then this one, the x here is bounded to this x. This x is bounded to this x. So these two x are unrelated. So in a sense, we can choose a different variable for this one as well, and which has the same meaning. So you can replace this part with for all y, qy. Because if you notice that this one will always have the same truth value of this one. Is that okay? So for this whole thing, we can write in two different ways. For all x, px, and for all y, qy. Okay, is that okay? So probably let me give you an example. Okay, so what is it? For all x, so I have a shorthand notation here. Okay, something like this. Okay. So here, to understand this one, we first understand that this x is bounded by this for all x thing. So this part is one proposition. Okay? This is a propositional function, but the x here is bounded by this one. So this is a single proposition. Okay? Similarly, this is a propositional function, but this x is bounded by this x. So this is another proposition. Is that okay? And the value of the whole thing is we want to get the true value of this one, the true value of this one, and them together. Okay? And what is this? For every, suppose that the domain of x is integers. Let's try integers. So for all x not equal to 0, x cubed is not equal to 0, then we can understand that this would be true. Is that okay? Okay, because the only case for x cubed to be 0 is when x is 0. And we omit this case already. Okay. And this one, there exists x such that x is equal to 1. Yeah, true. So in that case, true and true will be equal to true. This is how we evaluate this one. Okay, good. Easy, right? Okay. Okay, test our understanding. So we have learned a lot of things already. Let's test. Yeah. So here, I have an English sentence. Every student in this class everyone has studied calculus. Okay. Okay, so this is a sentence. Now, suppose that we are going to use qx to denote this propositional function. X has studied calculus. Okay. Okay. Now, how to translate this one into this one? I have two parts. Okay, so the first part is, let's make it easy. We assume that the domain of the student, so we will create a domain of x to be, we just consider the students in this class. So this is the first question. And then the second question is, what if the domain is slightly different? Let's say this one is, we consider all the students in our school. Okay? So I hope you still remember the domain of x will make a difference to the value of the overall result. Okay, so here, the first one. Every student in this class has studied calculus. And then qx is x has studied calculus. Then how do you translate this? Very good. Okay. So this is simply for all x, qx. Is that okay? Is that okay? Because every x in the domain we should consider. Okay? How about the second one? Okay, the second one is still for all, because we are still looking at for every. Okay, for all x. But it should not be just for all x qx. it should be much complicated, a little bit more complicated. We need to find a way to just focus on the students in this class rather than the students in NTHU, right? So if I am using for all x qx, then this is not correct, because there could be students in NTHU who doesn't study calculus, right? But then for all the people here, we may all study calculus, and it will make this whole thing false, which is not intended. So what should we do? So we have qx here, and what? And they exist, and not exactly. Okay, not exactly. So for all x, okay, for all x, that means that we are looking at a student in the school, right? So we need to do the filtering, check whether the student is in our class or not. If it is not in our class, then okay, we don't care. But if it is in our class, we really want it to be having qx. So it is saying something like, if you translate it in English, it is like, for every people in our school, if that person is in our class, then he has studied calculus. This is what we need. So there's an if then. So here, this is like, x is in our class implies qx. Is that okay? Is that okay? So for every x, if x is in our class, he has studied qx. And if this statement is true for every x that you look at, for all the x that you look at, including the x that is in our class, including that the x that is in our school, you look at, and they give you all true, then it is true. Otherwise, it is false. Okay? And you will see that the only case that we can make this thing false is what? The only case that this statement is false is you really find someone in our class, but then this person has not studied calculus. Okay, this is the only case that is false. And it is the only case that this sentence is false. Is that okay?